Hello, I'm the Math King, and in this video, I wanted to talk about the derivative and how we use the derivative to measure rate of change. Um, so, as you watch this video, if you find that it's of any use to you, I ask that you like my video. And if you think my channel is of any use to you in general, I humbly submit that you could subscribe to my channel, and that would be a wonderful thing. Anyway, to open the discussion, I wanted to ask a question. If we look at the car in the photo, how fast do you think it's going? And some folk might say, hey, it looks like it's going pretty fast because you see all them streaks in the photo. It certainly looks like a fast moving car. If you're a cynical person, though, or a smart alecky person, you might argue, hey, its velocity is zero. It's not moving, right? Well, why would anyone say that? Well, for one thing, it's not moving, right? You don't see the car actually moving in the photo. You just see the image of a car that's stuck in the photo. It's not moving. The other thing is, how do you measure velocity? Well, um, you can measure velocity, let's say, by taking the displacement of an object, like this car, finding out how far it goes, and then dividing by the time it took to get there, right? But here's the thing: with a photo, you're literally taking a moment in time. You're capturing a moment in time, a snapshot, a literal snapshot of time, which by definition means that there is no time interval that goes by. Since there's no time interval that goes by, there's no time for a displacement to happen. At least in that moment, that car is not moving. Its velocity is zero, right? Okay, but what's wrong with that logic? Here's the problem: stuff moves. We know that in real life, that car would be moving, and anything else that we know and love, right? But if we follow the logic that I just described, well, the car's not moving in that particular moment. Why should it move in the next moment? Right? It shouldn't, right? It's not moving in this moment. It's not moving in the next moment. It's not moving in the moment after that, and so on and so forth. In other words, that car would not be moving anything that we normally associate with motion. Nothing would move. That doesn't make any sense. Our life experience involves movement. Mm. So, does that problem lie? And more importantly, how do we get unstuck? Well, here's the thing: the key is the fact that I was a little deceptive in the logic that I used. The problem's not as big as it seems because my assumption about how velocity is measured is wrong. What I actually described is something called average velocity. Average velocity is measured by taking a displacement or a change in position and then dividing by the time it takes to get there. Right? This doesn't tell us how to measure velocity at an instant, though, or what might otherwise be called instantaneous velocity, right? So we see where the problem in our logic is, or my logic, I guess, as the case may be. I asserted it, but it doesn't tell us how to actually solve the problem, which is how do you find that instantaneous velocity or the velocity of the car when that photo was taken, say, right? So a question like this was something that Sir Isaac Newton, who's called the father of classical mechanics, or what we otherwise know and love as physics in high school, this was the type of question he examined when he invented something called the differential calculus. So believe it or not, not only did Newton um, craft this subject, which many people hate in high school, but he also developed the math, which also many people hate, unfortunately, in both cases, with the belief that calculus would actually make physics easier to understand. But anyway, yeah. So in developing this math called the differential calculus, he was trying to answer that question: how do we measure the rate of change of position or velocity? How do we measure velocity at an instant in time? Um, So to examine this question more specifically, I've taken the liberty of using Desmos to generate a couple of graphs. The graph in red, we'll say, represents a young man's journey. He's visiting his mom on Mother's Day, and he gets in his car and he drives to his mom, who's 50 miles away. Right? In this graph, as you can see, the horizontal axis is a measure of time in hours. Right? So these numbers horizontally represent hours, and the vertical axis represents the position of his car in miles. Right? So as time goes by, he goes through displacement. At the start of his trip, um, he's at the 0.00. He hasn't moved yet. But then we start the clock and he takes off. And then by the end of his trip, he's at his mom's. If we look at those 2 points that I've highlighted in green, if we go with the notion that really average velocity is displacement over a change in time, his position is changed by 50 miles and the time is changed by 1 hour. So we can say that on average, or his average velocity for the entire trip was 50 miles per hour. That's his average velocity, which, by the way, you'll notice is also represented by the slope of that secant line that I drew connecting those two time position points. Okay, so there we go. So we know his average velocity the entire trip. One thing that we also might gather, though, however, from his trip, if we look at the graph of his trip, is that clearly his average velocity is not the same as the velocity at any moment in his trip, necessarily anyway. And we could see more specifically as time goes by, it looks like he's slowing down. For example, if we look at the first 15 minutes, in other words, when t goes from 0 to 0.25, he's only gone 25 miles. So he's gone 25 miles in that first 15 minutes. But in the next 15 minutes, in other words, from t goes to 0.25 to 0.5, he's only traveled a little more than 10 miles, right? He goes from, at t equals 15 minutes, he's at the 25 mile mark. But at t equaling 0.5 or 30 minutes, he's at 35.36. So in the first 15 minutes, he's traveled 25 miles. In the next 15 minutes, he's only traveled a little more than 10. So he's definitely slowing down throughout his journey. Right? So the logic would indicate, well, we know definitely his average velocity is generally not equal to his velocity at an instant. And he's likely to have a different instantaneous velocity at any instant that we measure it. So how do we measure it? So here's Newton's approach and the approach that we will take. If we don't know how to compute the velocity at an instant, we could approximate it by taking an average velocity, right? So let's say our instant of interest is the 15-minute mark. I want to find his velocity at that 15-minute mark, or when t is equal to 0.25. And again, I will highlight it right there. Right? I'll say that his instantaneous velocity there is roughly equal to the average velocity from that 15-minute mark to the 1 hour mark. Which, by the way, that average velocity, which we would compute by taking a displacement for a change in time, that would be the same as the slope of that blue secant line that I used to connect those 2 points of interest. And I say, okay, well, I'm going to approximate it using that, because if you look at the blue line, it's a rough approximation of his actual journey, right? It's not an exact approximation, but it's a rough approximation of his journey. So I'm going to go with that. I'm going to say that his velocity at the 15-minute mark is roughly equal to that average velocity from t equals 15 minutes or 0.25 hours to t is equal. And let's go ahead and compute that. So here's what we say. So the instantaneous velocity at 15 minutes, or when t is equal to 0.25 hours, is roughly equal to the average velocity from t is equal to 15 minutes or 0.25 hours to t 1 hour. And the way we compute that average velocity is its change in position or displacement over time. His final position at the hour mark is 50 miles. His initial position is 25. So that's the displacement or change in position. And the change in time, well, at the end, he's traveled for a time of 1 hour, but starting at the 15-minute, 25 hours, right? So this is his average velocity over that time interval, which we're saying is an approximation for his instantaneous velocity. When we do the math, we get roughly 33.3 miles per hour. So we're going with that for now. For the moment, we're deferring the question of how do we find his velocity at an instant. We're just saying, hey, we'll start out by approximating it. All right. So we understand that we're doing an approximation, but not only is it an approximation, it's probably not so great. It's probably a poor approximation because we know in reality he's slowing down throughout. And with that approximation, we've given him 45 minutes or the majority of his time traveling to slow down, right? So it's an approximation, not so great. How do we make it better? Well, the logic would indicate if the problem is that we gave him too much time to slow down, why don't we give him less time? In other words, why don't we shrink the time window over which we look? And this is exactly the approach that Newton took. So we're going to take that approach. So we're going to do a new approximation. We're still interested in finding the instantaneous velocity at that 15-minute mark. But what we're going to say now is that we're going to approximate it by taking the average velocity at that 15-minute mark or 0.25 hour mark from that time to 15 minutes later, or when t is equal to 0.5. So we're going to say that that average velocity is our new estimate of his instantaneous velocity at the 15-minute. So let me show you what that computation looks like. So we're saying that the velocity or the instantaneous velocity at 15 minutes or t equaling 0.25 hours is roughly equal to the average velocity from t equaling 15 minutes or 0.25 to t equaling 30 minutes or 0.5. So we've shrunk the time window, giving him less time to slow down. So the approximation we get definitely should be better. So let's see what we get. So that velocity would be, let's see, again, it's displacement over time. It looks like his final position at the 30-minute mark is 0.35 and some change. So it looks like 35 to the numbers on the graph, 35534. It's probably approximate. But we know at the 15-minute mark, he's exactly at 25. This again is miles. And we divide by the change in time. Well, the change in time this time is 30 minutes or 0.5 hours minus 15 minutes or 0.25 hours. And when we do the arithmetic on this, we get a new number. We get roughly 41.4 miles per hour. Okay. And I'm happy with that, or let's put it this way, I'm happier with that because it's faster. which I would expect his instantaneous velocity to be. It's faster than that 33 and 33.3 that we computed, right? So I'm encouraged with this. I think it's a better approximation because it stands to reason we've given him less time to slow down. Okay. Well, my goal though is not to find approximations for the instantaneous velocity. My goal and Newton's goal was to find the instantaneous velocity. So how do we get there? Well, we see the logic tells us that the smaller the time window that goes by, the better the approximation. So what if we could shrink the time window to nothing? If, going by that logic, if somehow we could do that, we would have the exact velocity at that 15-minute mark. Right? And this is the heart of what differential calculus is talking about. Right? We take that logic that we're talking about to its ridiculous extreme. Right? Still using average velocity as a pillar to compute this. Right? So what we're going to do now, we're going to try to come up with an expression for his velocity at 15 minutes, not an approximation, but an exact value. What we're going to say now is we're really shrinking the time window as much as we can. We're going to take a teeny tiny time window, delta t, right? And then take the average velocity between those two time instances, time going from 15 minutes or 0.25 hours to the new time, 0.25 plus delta t, right? Which would give us a new position, whatever the x value is, at 0.25 plus delta t. Unfortunately, I don't have an equation for the graph of the young man's journey, so I don't have a particular value for x, but let's say we were able to obtain that, right? Then what we could do is we could form an expression for the instantaneous velocity. And here's what that might look like. Right? Again, we want delta t to be 0, but we can't do that, right? Here's the expression for the average velocity. It would be displacement or the position at 0.25 plus delta t minus the position at 15 minutes, which is 25 over the change in time. We can't let delta t be 0 because we then have a divide by 0 mistake. So we do the next best thing, which is the heart of what calculus is all about, which is we take the limit of this fraction that I've encircled as delta t equals 0. In other words, if this fraction approaches a particular value, the closer that delta t equals 0, then the value it approaches is no longer an approximation, but it is the instantaneous velocity. Okay. Now, I said that this video is an illustration of something called a derivative as a rate of change calculator. Right? And velocity, by definition, is a rate of change of position. Right? So we formed an expression for calculating the velocity at 15 minutes for the son's trip to his mom on Mother's Day. Could we generalize that? Can we take the rate of change of some function f at some value x? Can we take the rate of change right there, that instantaneous rate of change? Well, if we can, we would do it in a similar way that we approached instantaneous velocity. We would find the average rate of change of the position function, and then we would take that average rate of change as the change in x, what I'm calling delta x here, goes to 0. So what does that look like? Well, so we're saying that the the instantaneous rate of change, which is otherwise known as the derivative, that instantaneous rate of change at x, and the notation for it is sometimes called f prime of x, that instantaneous rate of change is the average rate of change as the change in x approaches zero. We're taking the logic to its ridiculous extreme. We're using the average rate of change as an approximation point. But as soon as we shrink the change in x to zero, if we can somehow do that, it's no longer an approximation. And this is that thing that we know as the derivative. Notice how the expression is formed. We're taking the function value at the end minus the function value at the point of interest, and we're dividing by the change in x from here to there. When we simplify the denominator, we get just delta x. And so this expression here forms the heart of the derivative. It's known as the limit definition of the derivative. In a previous video, I've talked about the derivative as the slope at an instant or a particular point on the graph. And you see the same definition pop up that I've in a red box, but we see that this definition numerically is a tool that we can use to find the instantaneous rate of change of a function. So that's the numerical significance of the derivative. Again, I'm the Math King delivering this to you. So if you like my video, I encourage you to like it. And if you like my channel, I encourage you to subscribe. And I'll see you next time. Bye.